Hello again. This is video lecture 24.1, our first video lecture for chapter 24, and I am going to do it in two parts. Hopefully that will break it down into more manageable chunks for you, because we have some important ideas to introduce in chapter 24. The title of the chapter, Electric Potential. Not very helpful, not very informative. What does that mean? We're going to have to build up to what that means. So let me give you some big picture ideas first so that you can help understand, hopefully it will help you understand why we're introducing the ideas we are, kind of where we're going. So think back to last semester when we studied motion. Well, first we did kinematics. We just defined various quantities that were helpful in studying motion. Position, displacement, velocity, acceleration. But then we moved into dynamics. Why does a particle move the way it does? And for that we needed Newton's second law. A equals F net over m. And that's very powerful, and we could use it a lot to solve a lot of problems that involve motion. But it involves vectors, right? Acceleration and force are vectors, and you have to deal with components. And it can get messy mathematically. So that led us to introduce a whole new set of ideas to study motion, but that used scalars, namely work and energy. And we even had our first conservation law, conservation of energy. And that gave us more tools to study motion, and could help us solve some problems where using Newton's second law would be a nightmare. Okay, now that's where we are now in studying motion, but for charged particles. Yes, we could use Newton's second law, but we have to deal with vectors, and we have to deal with components, and solving Newton's second law may be a nightmare. If we could introduce work and energy ideas again, will that enable us to solve problems that using Newton's second law would be a nightmare? Let me show you exactly what I mean. Okay, let's look at a situation we've studied for quite a bit now for a while. Two charged particles. They're drawn right there. Q1 and Q2. They both happen to be positively charged. And let's say that we nail down particle 1 with its charge. We're not going to let it move. Nail it in. Bang, bang, bang. Particle 2 with its positive charge, we're going to carefully place right there where you see it, and then let go. Can you predict what will happen? We know enough physics, right, to predict, just describe in words what will happen. Once I let go of charge 2, will it not experience a force from charge 1? What will be the direction of that force on 2 due to 1? Did you say directly away from 1, like this? F2, 1. The electrostatic force on 2 due to 1 will be directly away. So when I let go of particle 2, will it not accelerate to our right, getting farther and farther away from particle 1? What if I want to study that motion in detail, quantitatively? What if I take the plus x axis to the right, say this distance between the 1 and 2 is just some distance x? How would I solve for the motion? Well, I certainly know Newton's second law, a sub x equals F net x over m. Remember that, old friend? We can use that, at least in principle. What do we use for the F net? We use Coulomb's law, because there's the force. It's electrostatic force. Force on 2 due to 1, and it's in the plus x direction. And that would be plus Q1 times Q2 over 4 pi epsilon 0 x squared. Okay, right? That's Coulomb's law. And then I have to remember to divide by the m. And I mean the m of particle 2. And that would tell me the acceleration of the particle. That's the formula for it. It's Newton. The problem with it, though, is that the acceleration depends upon that x distance you see up there. And that's changing, isn't it? The minute I let go of particle 2, it accelerates to the right. So certainly the acceleration is not constant. And we cannot use any of the constant acceleration equations to study this motion. Okay, so guess what? It's a nightmare to try to figure out exactly where will particle 2 be at any given time, because the acceleration is not constant. But if we can introduce work and energy ideas, that might give us another set of tools that would enable us to study that motion of particle 2. And that's what we're going to do in this chapter. We're going to use work and energy ideas to study the motion of charged particles that experience electrostatic forces. All right, now here's the first thing to build upon. Again, an idea from last semester, but it's been a while. One of the important concepts when we studied energy and work last semester was the concept of what's called a conservative force. Those were very special forces for which the work done by these forces, is independent of the path that the particle takes from one point to another. Just what's the starting point and the ending point. You don't have to worry about the path it takes. The special forces for which their work is path independent are called conservative forces. We had 2 conservative forces last semester: the gravitational force and the spring force. And for every conservative force, there is a corresponding potential energy function. There was a function ugrav, m times g times y, the y coordinate above the ground or above your reference point. And there was an elastic potential energy that went with the spring force, 1/2 kx squared, where k is that spring constant. Those formulas should ring a bell a little bit from last semester. Okay, I'm now going to state something without mathematical proof. Okay, so you'll just have to believe me. But here I'm going to state it. The electrostatic force that we're talking about between these 2 charged particles here is one of those special forces called a conservative force. Okay? And if that's true, that means there is a corresponding electrostatic potential energy, okay, that we could denote U, or U electric. So just like we had a U gravitational and a U elastic, we'll now have a U electric, because we have our third conservative force, the electrostatic force between or on one charged particle due to another. So that's going to be the main topic of this video, introducing the concept of electrostatic potential energy. But I'll give you a little bit of a heads up for the part 2 of the video lecture. Okay? All right. This is building on the concepts from chapter 22. In chapter 22, we introduced electrostatic field, E, which by definition was electrostatic force per unit charge. E arrow is F electric arrow over Q. And in fact, the units of E are Newton per Coulomb, force over charge. All right, we introduced that in chapter 22. Electrostatic field, often called just electric field, is electrostatic force per unit charge. Okay? And that's a useful idea. So we're going to use that idea here as well. Okay? In this chapter, we're going to introduce a quantity that is electrostatic potential energy per unit charge. In other words, U electric over Q, with units of joule per Coulomb, energy over charge. And we're going to give this quantity its own name, electrostatic potential energy per unit charge. And the name for it is the name for the title of this chapter, electrostatic potential. I do not like the name. I doubt if there are any physicists really who like the name. It's a very bad name. It's confusing and it doesn't tell you anything. But that's the name because everybody's stuck with it. Electrostatic potential is electrostatic potential energy per unit charge. I'm not even going to write the symbol for it yet. I'm going to wait for that, okay? I'm just telling you the ideas now, okay? So we're going to have in this chapter the concept of electrostatic potential energy, symbol U, elec, and electrostatic potential, with symbol to be stated later, as electrostatic potential energy per unit charge. Okay? All right, that's the big picture. So let's start chapter 24, section 1. Title of that section is electric potential, but that concept is coming up in the second video lecture here. I'm going to start by talking about electrostatic potential energy, and I'm even going to limit myself to the special case where I'm dealing with a uniform electric field. So let's talk about what I'm thinking about here. Let's consider the situation where we have a uniform electric field. One way to produce that uniform electric field is by taking two flat, parallel, insulating sheets with equal and opposite surface charge densities, plus sigma and minus sigma. And that's shown over here in the figure on the right, labeled B. The upper sheet is the positively charged sheet with a uniform charge per unit area plus sigma, and the lower sheet is the negatively charged sheet with a uniform charge per unit area negative sigma. And using Gauss's law and what's called the principle of superposition, which I talked about in a video lecture in chapter 23, you can show that in the region between the sheets, right in here, in this region in between the two sheets, there is a uniform electric field, E, same at every point in that region, that is directed away from the positively charged sheet and toward the negatively charged sheet, which in our case is downward, which is negative y. Now the formula for that field, E magnitude, is sigma over epsilon 0. You use Gauss's law to show that. Chapter 23, section 5. Okay? But I'm just now going to take that as given that I have a uniform electric field between those sheets pointing downward, negative y. Now on the left, I have a plain old vanilla application that is analogous. The situation near Earth's surface where I have a uniform gravitational field, G arrow, directed downward, negative y. Okay? Gravitational field strength, G arrow, in Newton per kilogram. And yes, its value is 9.8 when you're near Earth's surface. 9.8, its magnitude, Newton per kilogram. I have on the right, the electrostatic equivalent to the picture on the left, the gravitational case. It's just, I say that because it's sometimes handy when you're dealing with the electrostatic case to refer back to the gravitational analog, because you're more comfortable with that. All right, so let's focus on the electrostatic situation, and I'm going to consider two cases. Case 1. Let's take a charged particle, proton. Remember the charge on a proton? Q is plus little e, e being the universal charge quantum, 1.6 times 10 to the minus 19 coulombs. That's the charge a proton has. And let's take it and put it at the point marked A on our figure on the right. See it there, marked A? And just let go of it. That's all we have to do in this case. And it will move from A toward point B. Now, it will actually pass through point B. I don't care about that right now. Let's just look at it moving from A to B. Okay? And the distance between points A and B is h, as you can see there. The proton will do that quite naturally. It will move from point A to point B in the presence of that electrostatic field because there's an electrostatic force acting on it due to the electric field. Remember our old friend? If I immerse a particle of charge Q in an electrostatic field E, the force on the particle will be Q times E. And RQ in this case is little e for a proton. So little e times big E. And big E is down, so F electric is down. okay, on the proton that I'm talking about. With me so far? So here's our question. What can we say about the work done on the proton by this electric force? Is it a positive scalar quantity, a negative scalar quantity, or is it zero? Pause the video, think about that, get an idea please, and then come back. Did you say the work done by the electric force on the proton in this case is positive? Let's talk about why. Now this is going to have to take a little bit of a refresher in our memory. How do we even calculate the work done by a force? Well, there's one bit of good news. In this case, the force is constant. The force on the proton is constant. How do I know that? From that formula, there or there. Because the proton is immersed in a uniform electric field, the same everywhere. So the force is the same everywhere. When the force is constant, the formula for calculating its work is the force dotted into the displacement. That's a dot product of two vectors. Let me draw them over here. Let me draw a little bit more over here to the side. Here's point A. Here's point B. Let's draw the displacement vector, the delta R. Just points in a straight line from starting to ending, delta R. Which way does the F electric point? Can you see that? I'll just draw it over here to the side. The F electric on the proton points straight down. Notice then the F electric and the delta R are exactly in the same direction. So when we write down the symbolic expression for this W, we will have the magnitude of F electric times the magnitude of delta R times the cosine of the angle between F electric and delta R when they're drawn with a common tail. They both point in the same direction. So the angle between them is 0 degrees. So what I get is, let me write it down here. Magnitude of F electric, little e times magnitude big E, magnitude of the displacement, h, times the cosine of 0, which is 1. Everything there is positive. The force does positive work because it's in the same direction as the displacement. Okay? All right, let's consider another case, case 2. This time, we're going to take a negatively charged particle, an electron. So its Q is negative little e. That's the charge on an electron. And we're going to have the electron move from point A to point B in the presence of this electrostatic field. Now, this is a little tricky. Let me get myself some room here. Okay? Let's draw a picture over here to the side. The A and the B points. And I am definitely going to have the electron move from A to B. So that's its displacement. But let's think about the direction of the F electric. Well, start with Q times E arrow, but now put in the Q, negative little e times E arrow. And this tells me, this negative sign, that the direction of F electric and the direction of E arrow are opposite. And E arrow is down. So the F electric, the force on the electron, is up. Well, wait then. How is the electron going to move from A to B? The electric force is upwards. It's not going to want to move from A to B, is it? Fine. I'll drag it, kicking and screaming, from A to B. I can do that. It's just an electron. Okay? But that's how you can get it to go from A to B. I mean, it's possible. You have to drag it. Fine. But that's what's going to happen then. Here's the question, though. As this electric force acts on the electron due to the electric field, what can we say about the work done on the electron by that force? Is it a positive scalar, a negative scalar, or is it 0? Pause the video, think about it, and then come back. Okay, did you say in this case that the work done by the electric force is a negative quantity? Let's make sure we can explain Why? Start with W electric equals F electric dot delta R. And now use the property of the dot product. Magnitude F electric, magnitude delta R, cosine of the angle between F electric and delta R. F electric points up, delta R points down. Exactly opposite directions, right? So what's that angle between them? Because that's what I have to take the cosine of. Did you say 180 degrees? And what's the cosine of 180 degrees? Did you say -1? So what's our expression for the electric work on the electron? Negative magnitude F electric times magnitude delta R. All right, that's negative. Now, magnitude of F electric, so just little e times magnitude delta R, magnitude E, and the magnitude of delta R is H. Note then, it is just the negative of the work that was done on the proton. Okay? Okay, so we have to deal with both cases, positive charge particle moving in an electric field and negative charge. But if the field is uniform, it's not too hard to calculate the work done by the electric force. Now let's go through the gravitational case as well, on the left side, okay? Let's have a mass that's in a uniform gravitational field down, and we're going to release it at a point A and let it move to a point B. Okay, so let's do the gravitational case. So we've got a uniform, that's the ground, gravitational field, G arrow, and we're going to take a particle with some mass, m, and we're going to release it from point A and let it move to point B, like so. So its displacement would be downward, delta R. And what would be the formula for the gravitational force on it as an actual vector? Well, if gravitational field is force per unit mass, and my particle has a mass m, I multiply that field by m, and I've got the gravitational force. And of course, that's our old friend mg. And of course, mass is positive. So the direction of F grav is the same as the direction of g. And of course, F grav is vertically down. And it's uniform, right? Because g is uniform. So W grav is F grav dot delta R. So let's not skip any steps. Properties of scalar product. Magnitude F grav, magnitude delta R, cosine of the angle between F grav and delta R. They both point downward, same direction. The angle between them is 0. Cosine of 0 degrees is +1. Magnitude of F grav is just m times magnitude g, and magnitude of delta R is h. And it's positive, isn't it? Good old just mgh. That's the work done by the gravitational force on the mass as it goes down. And that's the only case you have to deal with in the gravitational situation, right? There is no negative mass. Otherwise, we'd have to deal with that too, wouldn't we? But there is no such thing in nature. Okay? All right, so the gravitational force does positive work on a mass as it moves downward in the direction of the gravitational field. Now here's another idea from the last semester. In addition to the work done by the gravitational force, W grav, which by the way, if it's all right with you, I'm just going to denote WG, we also had gravitational potential energy. And for our particle moving from A to B, the gravitational potential energy changes. And there was a very important relationship between that change in gravitational potential energy, delta U grav, and this work done by the gravitational force, W grav. And that relationship was that the work done by the gravitational force, W grav, is just equal to the negative of the change of the gravitational potential energy. You can even, in fact, think of that as the defining relationship for U-grav. Okay? So if we use that, and our answer for W-grav, we can get a result for delta U-grav for this mass going from A to B. It's just negative mgh, right? And it went down. It's a negative number, so the gravitational potential energy decreased. Negative mgh by that amount. Now, another reminder from last semester. The formula we had in general for delta U-grav was m times g times delta y. So comparing these two expressions here, I conclude that for them to be consistent, I must think of the delta y for the particle as being negative h. Well, that's exactly what happened. It went downward by an amount h. That's the gravitational case. Notice then, because gravitational force was conservative, we could have a gravitational potential energy. When the particle moves from A to B, we can talk about the change in the gravitational potential energy, right? All right, now think back to the electrostatic case. We have a uniform electrostatic field giving us a uniform electrostatic force. I'm just telling you that the electrostatic force is conservative. So as a charged particle moves from A to B, because of the electrostatic force, we can talk about a change in electrostatic potential energy. And I want to talk about that now. And it's going to be, we're going to figure out the formula for it in analogy to that formula right there in the gravitational case. So here we go. All right, next idea. If a particle of charge Q moves in a uniform electric field E arrow, the electrostatic work done on the particle is W electric is F electric dot delta R. I was just using that. For the F electric, use Q times E. You can factor the Q and you write it like that. Q times E dot delta R. That's a nice little handy formula for the work done in a uniform electric field on a particle of charge Q. And the sign of that W electric, that work, depends on two things. The sign of the charge Q and the angle between E and delta R. Because that formula for W electric, if I expand it out, would be Q times magnitude E times magnitude dr times the cosine of what I'll call phi, which is the angle between the E and the delta R. Delta R. All right, here comes the next idea. The electric work done is path independent because the displacement delta R is path independent. That I can show you with this picture right here. There's the point A and the point B. There's the delta R connecting A and B. Straight line connecting A and B. There's the uniform electrostatic field E pointing down. Now you could have any number of paths that you want for your charged particle to go from A to B. You may have to drag the particle along those paths, but you could do it. You could take the particle from A to B along path 1, like that, or from A to B along path 2, like that, or from A to B along path 3, like that, or any other path you could think of connecting A and B. But no matter what actual path, the displacement vector delta R still is just an arrow pointing from A to B. And so the displacement delta R is the same for all paths between A and B. But delta R is in the formula for the work. Right there, delta R. And the E is the same. So the W electric is the same for all paths between A and B. But then that means the electrostatic force for a uniform electric field is a conservative force. That means we can define an electrostatic potential energy function, or the electrostatic potential energy change, as our particle of charge Q moves from A to B. Here we go. Defining the electrostatic potential energy change for a particle of charge Q moving from A to B in a uniform electric field. Remember W grav equals negative delta U grav? Well, W electric is negative delta U electric. That's the defining relationship for U electric. And there's the formula right up there. Right there. For W electric in a uniform electric field, particle of charge Q. So, in a uniform electric field, the delta U electric for a particle of charge Q that moves from point A to point B is negative Q times E dot delta R. And we can use that formula to calculate how much the electrostatic potential energy changes when our charged particle moves between 2 points in a uniform field. So let's practice with that a little bit. And then that will bring us to the end of the part 1 of this video lecture. Okay, so on this last slide, we're just going to practice using that expression right there. Can you see it? Just a little bit, okay? All right, so I'm still considering that I have a uniform electric field pointing down. And I've got 3 locations or 3 levels within that field. A, and below that B, and below that C. And I'm going to do some little thought experiments where I'm going to take a charged particle and let it move in this uniform field. Let's start out, I think it's easier conceptually, to start with a positively charged particle. Let's start with a positively charged particle, for example, a proton. That means we know what the Q is for our particle, plus little e. And let's release it at level B, like right there. Okay? Our proton at level B. You see which way it's going to move naturally because of the electrostatic force? Look at the direction of E. What's the direction of F, electric, on our proton? Did you say down? Same direction as E, because the proton is positively charged. So when I let go, the proton will move naturally from B to C, this way, and end up passing through point C. But I'm just going to look at B to C. What's the sign of the change in the electric potential energy for this trip? What is the sign of delta U electric? Positive? Does the electric potential energy go up, increase? Or is delta U electric a negative value, meaning the electric potential energy goes down? Well, let's think about it. Okay? Delta U electric is negative Q times E dot delta R. Let's put in the signs and just do everything exactly correctly. Negative little e, because the Q is little e, and then magnitude electric field, magnitude displacement, cosine of the appropriate angle. All right, here's the delta R, downward. The E is downward, so the angle between them is 0 degrees. Cosine of 0 degrees is positive 1. This is negative magnitude big E times magnitude delta R. Key thing, negative. The electric potential energy decreases. Oh, actually, it tells us that, doesn't it? Decreasing U electric is down. See the red arrow pointing down? The electron will, if you just let go at level B, will naturally move down to level C. And in so doing, will decrease its electrostatic potential energy. Note the same thing would happen in the gravitational case, where I have a uniform gravitational field downward, and I take a particle of mass m and I just let go at level B. Then yes, it will move to level C, and it will decrease its gravitational potential energy. Okay, now let's look at case 2. Again, we have a positively charged particle, let's say a proton. And now we're going to take it from level B up to level A, this way. We'll have to drag it against the electric force to do it, but fine, we'll do that. Okay? What is the sign of delta U electric? In that case, what happens to the electric potential energy in this situation? Dragging a proton from B to A. Does the electric potential energy go up? Go down? Let's work it out. For case 2, delta U electric is negative Q times E dot delta R. That's negative little e, magnitude big E, magnitude delta R, cosine of what angle? Well, now the delta R points up, but the E points down. Exactly opposite. So the angle cosine that I have to use is 180 degrees. Remember, the cosine of 180 degrees is negative 1. So altogether, this turns out to be plus little e, magnitude big E, magnitude delta R, which is clearly positive. The electric potential energy has increased when I drag the proton from B to A. Okay? Well, there's a gravitational analog to this. Again, you've got a uniform gravitational field down. You've got a particle at level B with some mass m. If you want it to go to a higher level A, you have to pull it up there, don't you? You have to drag it to higher level A, but you will have a larger gravitational potential energy when you do. So the positively charged case here is exactly analogous to the case with gravity. But now let's look at another situation, situation 3. Let's have a negatively charged particle. How about an electron? Then the Q is negative little e for case 3, right? Can't see that very well, can you? The Q is negative little e for case 3. And we're going to release the electron at point B, and it's going to move, note, naturally, from B to A, this way, until we get up here. You see how we know it's going to do that? Naturally, go from B to A, go higher. Because it's a negatively charged particle, so the F electric acting on it is opposite to the electric field E, and the E is down. So now here's the question, though. What's the sign of delta U electric in this case? Well, let's work it out. Negative Q times E dot delta R. Negative, okay, now be careful. The Q is negative little e. Then I have magnitude of electric field, magnitude of delta R, cosine of the appropriate angle. Well, let's think about this. The delta R is up for my electron here. But the E is down. So what's the angle between them? 180 degrees. Cosine of 180 degrees is negative 1. Note then that there are 3 negatives altogether, so that ends up being negative. Little e, big E, delta R. It's negative. The electric potential energy decreased. Okay? Even though the negative charge went up. Well, the point is it went against the electric field, and for a negative charge, that's the natural way to go. And if it happens naturally, the potential energy decreases, as the red arrow, that big red arrow there shows. All right, I'm going to let you try to figure out the last case for yourself. Suppose we take an electron and we drag it from B to C. It's not going to do it naturally, so we'll have to drag it from B to C. What's the sign of delta U electric in that case? It's not homework, it's not class engagement. Just think about it and see if you can figure it out, okay? So we have now introduced the concept in a certain situation of the uniform electrostatic field and a charged particle moving in that, but we've introduced the idea of electrostatic potential energy. All right, in video lecture 24.1 part 2, I'm going to now introduce the concept of electric potential. But that's all for this first video.